Welcome to today's Explainer. We're jumping right into a classic developer's dilemma found in a recent Haskell project log by a programmer named Ang. We are basically looking at that exact moment where pristine mathematical theory crashes headfirst into messy, real-world software engineering.
Okay, let's dive into this. You know that feeling, right? Have you ever refactored a piece of code, made it absolutely lightning fast on paper, and then suddenly realized you might have made it functionally fragile? Well, that's exactly the dilemma we're exploring today. When does a mathematically perfect optimization actually become your system's biggest liability?
Section 1. The Keyword Extraction Problem. So in Ang's pet Haskell project, the main goal was to map custom parser output directly over to the pandoc abstract syntax tree. And to extract the keywords, the original implementation used a standard list comprehension. It simply loops through the entire list of tokens, specifically filtering for a token called tmeta.
Now, structurally, because it filters the entire token's list of n elements, we're looking at an O of n operation. And while this is super readable, evaluating every single element means the execution time grows linearly with the input data. So if you've got a massive dataset, this theoretical bottleneck becomes a very real concern.
Section 2. Upgrading to O1 time. To completely bypass that linear loop, Ang proposed swapping out the list comprehension for pattern matching. By matching specifically on the head of the list, the code now only checks if the very first element is a tmeta token. It's kind of like it just checks the front door of the data structure without bothering to walk through the rest of the house.
And from an algorithmic standpoint, this is a massive win. The time complexity instantly drops to O of 1. Because it only checks that first position, it executes practically instantly. It is completely unbothered by whether the list has 10 items or 10 million.
Side by side, the elegant upgrade is totally clear. We go from a slower, linear list comprehension dragging through the entire list to a nimble pattern matching approach that checks only the head. In theory, that linear time trap has been completely avoided. Section 3. The Performance Plot Twist.
But wait, before we start popping the champagne, we really need to look at the real-world context of this specific Haskell project. The absolute crucial question is, did this brilliant refactor actually change anything in execution? Sure, we have an O of 1 operation now, but if there's only one tmeta token to begin with, did we actually improve performance at all? Looking closely at the data structure, Ang's specific parsing rules dictate that the metadata is always located right at the top of the file, meaning there is exactly one tmeta token in the entire list, and without fail, it is always the very first element.
Because the targeted token was always first and alone anyway, that ON penalty never actually dragged down performance in reality. The code would find it immediately regardless. Therefore, that beautiful mathematical performance gain on paper, yeah, it's completely an illusion. Section 4. The Risk of Brittle Code.
This brings us to the hidden danger introduced by optimizing for a very specific file structure.
Ang realized the massive catch.
What if the parsing rules evolve?
Actually, think about it. If the rules change so that each metadata field is its own individual tmeta token, instead of one big block at the start, matching only on the head of the list completely breaks. It would just grab the first field and ignore the rest, totally corrupting the extraction. By over-optimizing for speed, the code became dangerously brittle.
Section 5. The Final Verdict. So, what do you do when your mathematically optimized code turns out to be logically brittle? Well, here is how Ang resolved the dilemma in the project logs. For now, let's keep it this way, and we can revert to the original implementation if we ever change the parsing rule for metadata. It's a calculated risk, right? Keep the fast version for now, but actively document the potential need to revert to that slower yet way safer list comprehension later.
Which leaves us with this final thought to wrap up our explainer today. Is chasing O of 1 performance always worth the risk of writing brittle code? When does a perfect optimization become your code's biggest liability? It's a really delicate balance between algorithmic perfection and real-world resilience, and honestly, it's a question every software developer has to answer for themselves. Keep exploring those coding mysteries.